No worries.
Okay. Now recording. Okay. Any questions about homework 3? I'm always recording. If it's not recording, just remind me. I'll turn it on. Okay. So, okay, no questions. Okay, so then we can start new material then. Okay, so let's start chapter 3. So, chapter 3 is on conditional probability and independence. Okay. So 3.1 is on conditional probability. Okay, so let's A and B be events with the probability of B positive. The conditional probability of the occurrence of A given the occurrence of B is defined to be the quantity denoted by that symbol, and it's equal to the probability of AB divided by the probability of B. Okay, so for instance, if you're looking at the entire universal, if you're looking at the entire sample space S, and you're looking at a set A, and you're looking at a set B in the sample space, the conditional probability of A given B, what that is like is, since you're given B, right? So the B being here is saying that you're being given B. And so if you're being given B, then you're assuming that B happens, right? So your space becomes all B. So now you're only looking inside of B. There's nothing other than B now. So if you're going to limit, you're now limiting yourself to only the set B. And then you're saying, what's the probability of A given B? So then what that means is you're asking yourself, what is the probability of A happening given that B happens? And so that probability, and so that's why this is equal to the probability of A intersection B, probability of AB, divided by the probability of B. Because now you're only living in the space B, and you're asking yourself, what's the likelihood of A happening given that you're in B? And so that's the probability of A intersection B divided by the probability of B. Okay? The given event is the right of the vertical line. That's the condition. And so that's why it's called a conditional probability. Okay. Okay, so that is called the conditional probability of A given B. That's how you say it in words. 3.1.2 is use of the conditional probability. So let's look at an example. So this is example 3.1. A box contains 10 balls. Good. Okay, you can see the screen, I'm assuming. A box contains 10 balls. 6 are black and 4 white. 4 of the black balls have smooth surfaces, and 2 are rough. Okay, one white ball has a smooth surface and three are rough. Consider an experiment in which a ball is selected at random from the box where each ball is equally likely to be chosen. Let B, W, and R denote the events of selecting a black, white, and rough ball, respectively. A, find the probability of a black ball, selecting a black ball, find the probability of selecting a white ball, and find the probability of selecting a rough ball, find the probability of selecting a black rough ball, and find the probability of selecting a white rough ball. Okay, instead of words, I'm using the notation here for these 5 probabilities. Okay, so let's find each probability. Okay, so the probability of a black ball is just the number of black balls divided by the total number of balls. And so the number of black balls is 6 divided by 10, the total number of balls. And so as a decimal, that's 0.6. The probability of a white ball is equal to the number of white balls divided by the total number of balls. And so the number of white balls is just 4 divided by the total number of balls. That's 4/10. As a decimal, that's 0.4. Okay, it's good practice to calculate easy probabilities like this. It's good practice of the notation. Okay, so the probability of a rough ball is the number of rough balls divided by the total number of balls. This is equal to, well, what are the number of rough balls? There are 2 black rough balls and there are 3 white rough balls. There are a total of 5 rough balls divided by the 10, the total number of balls, that's 0.5. The probability of selecting a black rough ball is equal to the number of black rough balls divided by the total number of balls. The number of black rough balls, well, 4 of the black balls have smooth surfaces and 2 are rough. So there are 2 black rough balls divided by the total number of balls, which is 10, and that's 0.2 is the decimal. And the last one is the probability of a white rough ball, which is the number of white rough balls divided by the total number of balls. And so that's equal to the number of white rough balls. So there are 3 rough white balls divided by 10, the total number of balls, that's 0.3. Okay, so those are those 5 probabilities. And so part A is just finding those 5 probabilities, and that's just from the earlier theorem, and so there's nothing new here in part A. Okay, in part B, now we're going to ask if the ball selected is rough, what are the chances that it is white? Okay, so one question is, what is the problem asking you to find, right? Use notation to represent the probability you are asked to calculate. Okay, so that's what I want you to do for me right now. So don't say it out loud, just do it to yourself. Don't write it in the chat either. Just tell me what the probability that you don't have to calculate it, just what is the probability, what is the event, what the probability of what event is what the question's asking you to find. Okay, tell me what probability you're being asked to find using the notation of the problem, using B, W, R, and conditional probability. Right, we have conditional probability here. Okay, So do that on your own for a minute, maybe. Don't say anything out loud. Don't say anything out loud, Krishan. So, okay, keep trying to figure it out. I'm going to highlight some things. I still want you to figure out yourself. I'm going to help you by just highlighting something. Okay, so Anna, I'm going to ask you in a minute, maybe a little less than a minute, what your answer is. Okay, Anna, do you want to share with us? It sounded like you wanted to say what your answer was.
Oh, sure. Yeah. Oh, can I speak up?
Yeah.
Oh, okay. So I'm not sure if it's right, but I was thinking that the problem is asking us to find like basically the like probability if we choose only rough balls, like what is the probability that it's going to be white? So we have to divide the number of white rough balls by the number of the whole number of rough balls, right? So
Let's shorten your answer. Tell me what the type inside the parentheses there in the probability.
Oh, yeah. So it's going to be WR.
Like that?
Yes.
You're so close, but it's not WR. It's W vertical line.
Wait.
You're not finding the probability that it's W and rough. You want the probability that given the ball is rough, that it's white.
Okay.
Does that make sense?
Yeah. It makes sense. Yeah.
See the R there, right?
Yes.
The R there is the given, right?
Okay. Yes.
When you said if, it says if the ball selected is rough. That means that the given is after the if, right?
Oh, okay. Yes, it makes sense. Yes.
Right? If I say if it is going to rain, then you're going to get wet. The given is that it's going to rain.
Oh yeah, sorry. I think I just joined later. So it's gonna be like this conditional probability that you were talking about, right?
Wait, what?
So it's like the new topic, right? The one that you were discussing. That's why it's vertical line. Because I think I skipped the first, like I joined a little later. So it's like conditional probability, right?
Oh, yeah.
Okay, I was like, oh, this looks new.
Yeah, let A and B be events with the probability B being positive. The conditional probability of the occurrence of A given the occurrence of B is defined to be this quantity.
Right. Yeah. But I mean, I got the point, but I didn't know how to like write the notation. But
okay, you don't always have to be given the definition of something to understand how it works. So you're seeing it here, right? So
but anyway, I think like we have to divide 3 by 5, right? The number of white rough balls by the number of rough balls in general.
Okay, you should look at the definition, right? So probability of A given B is the probability of A and B divided by the probability of B.
Yes.
So when you're looking at the probability of A given B, you're given B, so you're only living in the space B, and you're saying what's the probability of A? Then the only occurrence of A that matters is something that's also in B. So it's the probability of AB divided by the probability.
Right. Yes. Correct.
Does that make sense?
Yes.
Okay. So if there was if there were 2 things here, and there were 3 things here, and there were 5
Yes.
things here, then
Right.
this probability would be 3/5.
Yes, exactly.
I mean 3/8.
0.6.
3/8.
Oh, okay. Okay,
Because
got it.
3 of the red things are in the
Wait,
B.
oh, wasn't it? Okay, I got it.
Yeah, well, okay, I guess it would be 3/10 divided by 8/10, and then that would be 3/8. I just got rid of the denominator.
Okay, yes, it makes sense.
That makes sense?
Yeah.
Okay. Might be a little nervous with the camera on, but yeah, okay. So yeah, that's the idea. So maybe delete the 3. Okay. Thank you for participating. Good. Okay, so I'm gonna put this back to the way it was. I go back here. Good. Okay, so if the bowl selected is rough, so the event of it being rough is the given, and then the white is what you're asked to find. So you want to find the probability of being. You still are looking for the probability that's white, but you're given that the bowl is rough, and so that means that the probability you're asked to calculate is that. And so now it's just a matter of calculating that probability. Is this automatic? Okay, good. Okay, so now you just calculate this probability, and after you do that, it's done. So this is the probability that it is white and rough, divided by the probability that the bowl is rough. And so then to calculate this, and so I should point out that here in this definition, note that when you say that the probability of A given B is equal to that, that means it's equal to the number of sample points in the event AB divided by the total number of sample points in the space, divided by the number of sample points in the event B divided by the total number of sample points in the space, because these are the probabilities of in the numerator and denominator. Now, the capital N cancels, and so this is the same thing as saying the number of elements in the set AB divided by the number of elements in the event B. Okay, so when you're calculating the probability of A given B, there's also a shortcut where instead of having each probabilities, you can count the number of elements in AB and divide it by the number of elements in B. Okay, and so sometimes, not always, sometimes this is a better way to calculate the probability of A given B using this. Okay, and so that means you can calculate the probability of A given B by finding this quantity instead. All right. So here, sorry for going fast, so that you can say this is the number of white rough balls divided by the number of rough balls, instead of worrying about the probabilities of each. And so the number of white rough balls, though I guess they're leading you to do this anyway. So, okay, well that's just a side note. So we can just plug it in. Okay, so the probability of white and rough is 0.3, and it's divided by the probability of red, which is 0.5. Okay, and so then that's 3/5, and that's equal to 0.6, and that's the answer. Okay, any questions about that? Okay, good. Okay, so that's one example of conditional probability. Suppose that 5 cards are to be drawn at random from a standard 52 card deck. If all the cards are equally likely to be drawn, just assume all the cards you feel like to be drawn. If all the cards drawn are red, what is the probability that all of them are hearts? Okay, so suppose that 5 cards be drawn at random from a standard 52 card deck. Assume all the cards are equally likely to be drawn. If all the cards drawn are red, what is the probability that all of them are hearts? Right, so this is again a conditional probability problem. So recognize first that this is a conditional probability question. Okay, you were asked to find a conditional probability. And so what is that probability, right? That's the question. So conditional probability has an event on the left and on the right, right? We have a given probability on the right, and then on the left is the probability we're trying to find. So one keyword is the word if. So I'm going to enlarge the word if and bold it, okay? So in a conditional probability problem, the word if is really important. Okay, and the word if does not have to appear at the beginning of a sentence. It could be in the middle of a sentence. Okay, it's not about where something is in the sentence. It's about the context. It's about what's happening in the sentence. Okay, so in English, you can have a sentence, and you could switch the order of the sentence and then still say the same thing, right? If you were listening to Yoda talk, he would say like the end of the sentence at the beginning and the beginning of the sentence at the end, but he's saying the same thing. And so that can happen in a math problem where you could change the order of things. So it's not about where something is, it's about how it's being said. So the word if is a key word. It says if all the cards drawn are red. And so I'm going to put this in green. I was going to put in red, but it's referring to red, and I want to just call it something else. So if all the cards drawn are red. So what's after the if is 99.99% of the time a given, and it may in fact be always. So this is the given event. So let capital R equal the event of all 5 cards being red. Then R is the given event in your conditional probability. It's what's to the right of that vertical line because it's the event after the word if. It says if all the cards drawn are red, and R is the event of all 5 cards being red. And then it says what is the probability that all of them are hearts. And so all of them are hearts. I'm going to call that blue. Okay, and so I'm going to let H equal the event of all 5 cards being hearts. H for hearts, R for red. So the question is saying what is the probability that all of them are hearts? And so the fact that it says what is the probability that, I'm also going to make that in big font. And so I'm going to put that in big font also. It's saying what is the probability that, right? So if you're asking what probability you're trying to find, that's the probability you want. You're finding the probability that all of them are hearts. So to the left of the vertical line is H because that's the probability you want to find. And to the right is the given event because all the cards drawn are red is the event. It's the given event. It's what's after if. Okay, so the green part is the given event, which is the all the cards are red. And so that's why it goes here. It's after the word if. What is the probability that cues the next thing all of them are hearts is the probability you want to find. And so that's why that's on the left of the vertical line. Does that make sense? Okay, so that's the probability you have to find. And then you just go by the definition. So the definition says this equals the probability of HR divided by the probability of R. Okay. And you can go by the Venn diagram I drew to understand what that formula means.
Professor, could you just change the color to red?
Because it's green.
Yeah. Like it
Well,
makes
the
more
reason why I have it green and not red is because I'm not drawing the attention to the fact that the event is all red cards. I'm drawing the attention to the fact that it's a given event. Okay.
Okay.
R is used because it's red. R for red. Okay. Maybe that's a little confusing. But the notation I'm using, what I'm writing down, matches perfectly. R for red, H for hearts, right? The colors are meant to denote the given event and the event you're trying to find the probability of. But it's not representing the event itself. Does that make sense, Cesar?
Yeah, so basically what you're saying is it's not really representing the color, but it's more representative of like the word itself.
It's representing what the event is. It's the given event.
Okay.
Does that make sense?
Yeah.
So that's why I didn't use red for hearts or red. I didn't want to use red at all for this because I just wanted to emphasize the statement itself and not what the statement was saying. Like, okay, that makes sense. Okay, so the probability of H and R. So it's the probability of that a card is both red and hearts. So remember, we can simplify this to the number of hearts that are red divided by the number of red. And so I usually like to do the easy part first. So the number of red cards is 26 because half the deck is red, right? The number of hearts that are red, well, all hearts are red, right? So counting the number of hearts that are both heart and red is the same as just counting the number of hearts, which is 13. There are 4 suits: hearts, clubs, diamonds, spades. Each of them have 13. And so the numerator is 13. So 13 over 26 is 1/2, and this is 0.5. That makes sense? The hardest part of the problem is just finding what the probability is that you're asked to calculate, right? Answering the question, what is the problem asking you to find, right? It's asking you to find this. Once you realize that, then it's better if you understand it. But as far as getting the answer right, you can just, if you were to apply the formula right there and then plug in the values of the numerator and denominator for probabilities, or to count each of these and do that, you would then get the answers. The hardest part is just recognizing what conditional probability the problem is asking you to find. And so hopefully that makes more sense. It really makes more sense the more examples you do. So if it's starting to make sense now, if you do more examples, it'll then make even more sense. Okay. Oh, wait, I'm sorry. Wait, I made a mistake. Sorry, I made a mistake. Yeah, I forgot what problem I was answering. It's saying there are 5 cards being drawn. Sorry, it's 5 cards, not 1 card. Okay, so let me just backtrack here. Okay, it's the number of 5 cards being drawn. 5 cards. 5. Okay, so there's 5 cards. Now I'm highlighting so many things that doesn't matter anymore. Okay, so we need to find these probabilities. It's a little more complicated. So the probability of getting 5 cards that are all hearts and red. Well, it's a 5-card hand, so that means that you have to think of just need to get this for a second. Okay, good. Okay, so this is the number of 5-card hands consisting entirely of hearts, of cards, both hearts and red. And the denominator is just the number of 5-card hands. Okay. So that's equal to, now, the denominator is the number of 5-card hands. And so if you have 52 cards in a deck, it's just the number of ways to choose 5 of them. The numerator is the number of 5-card hands consisting entirely of cards, both hearts and red. So for that, imagine having all 52 cards on the table. So I'm just redoing that. If you have all 52 cards on the table and you want to make a 5-card hand consisting of entirely of cards that are both hearts and red. So get rid of all the cards that are not both hearts and red. Well, all the black cards are gone. All the diamond cards are gone. You're left with only 13 cards, all the heart cards, which are also red. Okay? So you have 13 cards left that are both hearts and red. You want to make a 5-card hand from just those 13 cards. And so from those 13 cards, you want to choose 5 of them for your 5-card hand consisting entirely of cards of both hearts and red. And so there's 13, choose 5 number of ways to do that. So the probability of getting a 5-card hand, in which all the cards are hearts and red, is 13, choose 5, divided by 52, choose 5. That's that probability. Okay. Now, if you want to find the probability, the denominator, the probability of a hand all red, so what we're doing is calculating this. Okay. And it's a 5-card hand. Okay. The probability of a 5-card hand where all the cards are red, well, that's equal to the number of 5-card hands in which all cards are red divided by the number of 5-card hands. So what are the number of 5-card hands? It's still the same as before. You have 52 cards in the deck and you want to choose 5 of them for your 5-card hand. That's the number of ways to do that. The numerator is the number of 5-card hands in which all cards are red. So you start with all 52 cards on the table. You get rid of all the black cards. You're left with 26 red cards. Okay, you have 26 red cards. And so of those 26 red cards, you want to choose 5 of them for your 5-card hand consisting entirely of red cards. So there's 26 choose 5 ways to do that. And so that's the numerator. And so the probability of a 5-card hand where all the cards are red is 26 choose 5 divided by 52 choose 5. That's that probability. Okay, and so then you just plug these probabilities in here. And so you have this amount divided by this amount. But then the denominators cancel. So actually what happens is you end up with 13 choose 5 divided by 26 choose 5. And so that's the probability. And then when you calculate that, you get 0.0196. And that's the answer. Make sense? Any questions? Okay, if I'm going a little too fast, just let me know. Okay, so the notes are online. So if you can always get that after, right? Okay, so 3.2 is on Bayes' and other theorems on conditional probabilities. So the first theorem is theorem 3.1, and this theorem says that the probability of A prime given B is equal to 1 minus the probability of A given B. So the probability of A prime given B is equal to 1 minus the probability of A given B. Okay, so that's the theorem. And the proof of that theorem is just if you start with the probability of A prime given B, that's equal to P of A prime B divided by P of B from the definition. And that's equal to, well, in the numerator, P of A prime B is equal to P of B minus P of AB. And so how is that true? Well, I'm going to show on the whiteboard is P of A prime B is equal to P of B minus P of A B. The denominator is still the same, it's P of B. Ishan, do you have a question?
No, it was a comment.
Oh, okay. I wasn't quite, okay.
Hmm.
Okay, so P of A prime B is equal to P of B minus P of AB. So let's just explain this. Okay, so you have set A and you have set B. Okay, so if you have A prime B is this set right here. Right, this is A prime B. It's not an A and an B. So this set is equal to the set B minus the set, I'm going to put minus like this, minus AB. I'm going to stick with my old notation here. Okay, that's a minus. This is a minus. Means I'm just removing, right, the elements in AB from B. Okay, so A prime B, that green region, is if you take the entire circle B and you subtract from it AB, what's in here? Right, if you remove AB, if you remove the red part, if we remove this thing from B, you're left with the green part. And so what this implies is that the probability of A prime B is equal to the probability of B minus the probability of AB. Make sense? Okay, and so that's the numerator of over here. Okay, so you just place the numerator with that equal expression. And so now you divide, and so you get P of B divided by P of B minus P of AB divided by P of B. Okay, and then, well, P of B over P of B is 1, minus, well, P of AB over P of B is the probability of A given B. And that's it. Right? This is 1, and this, by the definition of conditional probability, is that. And so we just show us that P of A prime given B is equal to 1 minus P of A given B. That's what we want to find. So the proof is now done. Let me just leave that up. Okay. Oops, done. And so we have our first theorem of this section. The next theorem is theorem 3.2. And so it has parts to it. So I'm going to move this to the next page. Keep that there. P of AB is equal to P of A given B times P of B. And this is if P of B is positive. P of AB is also equal to P of A times P of B given A. That's a P. And this is if P of A is positive. Okay, so this is just from the fact that, oh, I need to plug in my laptop. This is just from the fact that the probability of B given A is the probability of AB divided by the probability of A. I'm going to write that down. Okay, so this is just from the fact that the probability of B given A is equal to the probability of AB divided by the probability of A. Okay, so since this is true, this is if P of A is positive. If P of A is positive, you can say this, and then you just cross multiply, and you get P of AB is equal to P of A times P of B given A. Okay, but you need P of A to be positive to do that. And so this is just a very similar reason. This is just from P of A given B is equal to P of AB divided by P of B. Okay, and that's if P of B is positive. And if P of B is positive, then P of the numerator here, P of AB, is equal to P of A given B times B. Okay, so B in this theorem says that the probability of ABC is equal to P of A times P of B given A times P of C given AB. And this is if the probability of AB is positive. Okay, so P of ABC, probability of ABC is equal to probability of A times probability of B given A times the probability of C given AB if P of AB is positive. And so how do you get this? Well, this is from the fact that, well, first, if given that P of AB is positive, what that actually implies that the probability of A is positive and the probability of B is positive. So where before we had one assumption, right, that if P of B is positive or if P of A is positive, here it looks like we're given one thing, that P of AB is positive, but actually we're really being given both are positive, because the only way that the probability of A and B is positive is if the probability of A is positive and the probability of B is positive. So sneakily, this actually giving me two assumptions here. And so, but you have the probability of AB is positive. And so since you have the probability of AB is positive, the probability of C given AB is equal to the probability of ABC, which is really probability of C and AB. I just changed the order. And this is divided by the probability of AB, right? And so that implies that the probability of ABC is equal to the probability of AB times the probability of C given AB. Okay, so now we know that this thing is equal to this times the probability of AB. And so what we just want is that this is equal to this, which is true. So, so the probability of B given A, well, actually, B given A. Okay, so the probability of AB is equal to the probability of A times the probability of B given A. This is if the probability of A is positive, right? This is from part A. Part A said this. And so we know that probability of A is positive because the probability of AB is positive. And so since the probability of A is positive, we know that the probability of AB is equal to the probability of A times the probability of B given A. And so here we had this already, right? So we already have this because this equals this implies that these two are equal. And so we have this, but now we have that the probability of AB is equal to this. And so I just substitute the probability of AB here for this. And then I multiply it still by the probability of C given AB. And now that's it. So we now have that the probability of ABC is equal to the probability of A times the probability of B given A times the probability of C given AB. And we're done. Okay, and so assuming that the probability of AB is positive, we now concluded this, and so we proved that. Okay, so this is the proof of B. Okay, so that's A and B of that theorem. Let's go to C. Okay, so the probability of A1, A2, A3, AN is equal to the probability of A1 times the probability of A2 given A1 times the probability of A3 given A1, A2 times times the probability of AN given A1, A2, A3, A minus 1. Okay, and then this is if the probability of A1, A2, A sub n minus 1 is positive. Okay, so this proof is done very similar to the proof I have here of B. And assuming that this probability is positive is again telling you the probability of all of those events in the product is positive. So just note, just like in the proof I showed you for B, note that the fact that assuming that this probability is positive, then that implies that the probability of A1 is positive, and the probability of A2 is positive, and and the probability of A sub n minus 1 is positive. Okay. Okay, so with this assumption, we know all of these probabilities are positive, and you can do what the other proof did, kind of working backwards, and you can start with the last thing. So you can start with this thing, this probability, and you can see it as the probability of this divided by the probability of A1, A2, AN minus 1. And then you somehow get all the other ones is equal to the probability of A1, A2, AN minus 1. And you just keep working backwards until you end up with the last one. Okay, so you start from the right and you work your way left until eventually you get the product of all these things is equal to this. Okay. You can do it by a method called mathematical induction, and you can get that. Okay, so next example. Suppose 60% of adults over 30 are college graduates. Further, suppose 80% of college graduates over 30 have incomes over $15,000. A, if a college graduate over 30 is selected at random from the community, what is the probability he or she has an income of $15,000? Okay, so let's start from the beginning. Suppose 60% of adults over 30 are college graduates. Further, suppose 80% of college graduates over 30 have incomes over $15,000. A, if a college graduate over 30 is selected at random from the community, what is the probability he or she has an income of $15,000 or less? Okay, so let's introduce some notation. So we're going to let A equal the event a person with an income of over $15,000 is selected. We're going to let the event B, let B equal the event a college graduate is selected. Okay, so A is a person with an income of over $15,000 is selected. B, the event a college graduate is selected. So the question is saying if a college graduate over 30 is selected at random from the community, what is the probability he or she has an income of $15,000 or less? So we are asked to find the probability of, well, what is the given, right? The word if cues us to the given, right? So if is the important word here. So if a college graduate over 30 is selected, so that's event B. Okay, college graduate over 30 is selected. Oh wait, sorry. Yeah, so everyone's over 30. Okay, so okay, so I'm leaving out the over 30 part. Okay, so so college graduate is event B, so that's a given. So that's what's after if. Yeah, so we're asked to find a conditional probability. So we're asked to find the conditional probability, and so the given in that conditional probability is the event B I defined here. And it's asking you what is the probability he or she. What is the probability? So that's the next. Those are the next keywords in the problem. What is the probability? And so after that says he or she has an income of 15,000 or less. So that's the probability I should find. The event that the person selected has an income of $15,000 or less. A is the event a person with an income of over 15,000 selected. And this event is 15,000 or less. And so this is the complement of that event. And so this is A prime. So we are asked to find the complement of this event, A prime. we want to know the probability that he or she has an income of 15,000 or less, or event A prime, given the event that a college graduate is selected, or given B. So we are asked to find the probability of A prime given B. Okay, using what we know from earlier in the lesson, we have that the probability of A prime given B is equal to 1 minus the probability of A given B. Right? So we know that the probability of A prime given B is equal to 1 minus the probability of A given B. So we have boiled the problem down to, we have reduced the problem to finding the probability of A given B and substituting it above into the equation just above. Okay, so we just need to find this probability, plug it in here. 1 minus that is the answer to the probability you're asked to find in A. And so the question is just, what's the probability of A given B? So the probability of A given B, by definition, is the probability of AB divided by the probability of B. Okay, and so what is that? So probability of AB is the probability that a person has an income of over $15,000 and is a college graduate. So you're given all this information here. So let's look at a Venn diagram. If you get stuck, it's good to look at a Venn diagram. So maybe I can copy this and bring this to the Venn diagram. We want to know the probability of A given B. Okay, so the entire sample space is really the people over 30. So the college graduates part, to remind you, the college graduates is event B. That's the event B. And A is the event of over 15,000. That's event A. Right, so it says, suppose 60% of adults over 30 are college graduates. So 60% is in circle B. 80% have incomes over 15,000. So 80% is in A and 60% is in B. So the probability of probability of A union B is equal to the probability of okay, so let me. We're just looking at sets A and B. That's everything. Okay, so A and B is everything. There's nothing else. So this is the probability of A plus the probability of B minus the probability of AB. And so this is 1. And so now we have that this is equal to the probability of A is 80% or 0.80. That's from here. Plus the probability of B, which is 60%, minus this probability. And so solving for this probability, you have that P of AB is equal to 0.8 plus 0.6 minus 1. And so that's equal to 0.4. So that 0.4 is 40%. So 40% are both college graduates and make over 15,000. So 40% are in the intersection. And so 40% are in the intersection, then that means that 60% are in B. There's a leftover of 20% here. And if A is 80%, then the rest of A is another 40%, because this is 40%, and then this is another 40 to make a total of 80. And so that's how you divide the percent here. And so when you want to find the probability of A prime given B, so the probability of A prime given B is equal to 1 minus the probability of A given B, which is equal to 1 minus the probability of AB divided by the probability of B, and that's equal to 1 minus, well, the probability of AB is 40%, divided by the probability of B, which is 60%. You could either add 40%, 20% here, or it was already given you that 60% was the probability of B, 60% of college graduates. And so this is equal to 1 minus, before simplifying, 4/6, this is less of a, you're multiplying numerator and denominator of this fraction by 10, you get 4/6. So that's equal to 2/6, which is 1/3, which is a decimal 0.33, the nearest hundredth. Okay, so the probability of A prime oh, wait a second, hold on. Okay, wait, I think, so maybe it's 40%. So okay, so then B, all right, so then for B, maybe I can fit B in here. So for part, I'm gonna type it here. That way I have the Venn diagram here. So for part B, it's what percent of adults over 30 in the community are college graduates and have incomes over $15,000. Okay, and so the probability of AB is equal to the probability of A given B times the probability of B. And so it's just our earlier answer times the probability of B. And so then that's is equal to 0.20, which is 20%. I think there's something wrong here. Wait, it says further, 80% of college graduates over 30 have, oh, sorry. Okay, so sorry about that. Okay, so A is over 15,000, but it says 80% of college graduates have incomes of 50,000. So that means that the probability of A given B is 0.80, because you're given B, you're given that they're college graduates. You're given that they're college graduates, and it's saying the probability that given that they're college graduates that they have incomes over 15,000 is 80%. So this is 80%, which means that here, really? Okay, so that means that here, probability of A prime given B is equal to 1 minus the probability of A given B, and that's equal to 1 minus 0.80, which is 0.20, which is 20%. Okay, and so that's it. That's all that is. Okay. You're given that probability right there. You don't need the Venn diagram. And then here, I just have to plug in the other probability. So this is saying find the probability of the events over 15,000. Find the probability of A. Okay, so you want to find the probability of college graduates and have incomes over 15,000. So that's P of AB. And so P of AB is equal to P of A times P. And P of A given B times the probability of B. And so then that's equal to the 80% from earlier, from the last problem, times the probability of B, which is 60%. And so you multiply those out and you get 0.48, and that's 48%. Okay, so what percent of adults over 30 are college graduates and have incomes over 15,000? So once the probability of A and B, that's the probability of A given B times the probability of B. Probability B is 60%, probability of A given B is given to you in the problem. This is given. That's the 80% that's given to you in the problem. And then this is by how we define B. Okay, and this is given to us. And so you just multiply them and you get that. And so that's B. All right. Any questions? Good. Okay, so oh, okay, good. Okay, good. Okay, and so I did that on the whiteboard. Okay, so The rest is on the whiteboard. Okay, let's do another problem. Okay, this is theorem 3.3. Let S be a sample space if B1, B2, ... Bn are mutually exclusive events such that S is equal to B1 union B2 union ... union Bn and the probability of B sub I is positive for I equals 1 to ... n, then for any event A of S, A, we have that the probability of A is equal to the probability of AB1 plus the probability of AB2 plus ... plus the probability of ABN. And we also have B, which says that the probability of A is equal to the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 plus ... plus the probability of A given Bn times the probability of Bn. Okay, so next class we will go over more of this theorem and the proof, but just before you go, what's happening here is you're just basically saying that if you have your sample space S, you're just partitioning it with these B's. So for instance, this could be B1, this could be B1, this could be B2, this could be B3, this could be B4, and then actually instead of B4, I'm going to put ... and then this is Bn. And so you're partitioning your sample space with these B's, and you're just saying for any event A, so if I took an event A, and let's say this event was here, and so this was event A, then I'm just saying that the probability of A is equal to the sum of the probabilities where you look at each individual, the part of it in each separate B. And so it's the probability of the purple region plus the probability of the blue region plus the probability of the orange region plus the probabilities of all of these regions in between, and then it's also plus the probability of this last region here. And so you just add up the probabilities of each of these different colors and the ones in between here, and you get the whole thing. And the purple region, you can think of that set as is AB1, right? It's the part of A that's in B1, so it's A intersection B1. And then this region is AB2. That's AB2. And then AB2. And then this region is AB3. And so forth. And the last region is ABN. And so you can think of A as equaling AB1, which is the purple region, union, the blue region, which is AB2, union, the orange region, which is AB3, union, dot, 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 union, the green region, which is A, B, N. And so you're just seeing the region A is the union of all these separate pieces where each piece is coming from a different B, from B1 to Bn, including all the ones in between. Okay, and so that's how this theorem is saying that the probability of A is equal to, probably here in A, the probability of A is equal to the sum of these. Because since A is equal to the union of these disjoint sets, these mutually exclusive events, AB1, AB2, and so forth, then the probability of A is equal to the sum of their respective probabilities, right? So since these events, subsets of the sample space, are mutually exclusive, all of these are mutually exclusive, the probability of A is equal to P of AB1 plus P of AB2 plus P of AB3 plus dot, 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 plus P of ABN. And so that's how you get that. Okay, so we're going to stop there and then we'll continue next class. Okay, I'm going to save the whiteboard. Okay, so the whiteboard is now saved, and stop the recording.